Uh, Hello, everyone. All who was patient enough for uh, still wait for us, and I'm very happy. I can announce the next episode of our Prague Seminar for Mathematical Physics. And today we uh, we invited Rudolf Šmolka from Czech Technical University, and Rudolf wanted to talk about some graded geometry, so we can look forward to the talk with the title Graded Vector Bundles as Graded Manifolds. So Rudolf, thank you for coming, and we're looking forward to your performance.
Thank you so much for the great introduction. Right, so before I start, first thing, if you have any questions, anytime, just ask. I can't promise that I will know the answer, but luckily we have my supervisor and Misaki here.
No.
Also, Branyo might be here as well. So those, if I don't know the answer, maybe they will. So feel free to ask anything. Okay, so today I want to talk about graded vector bundles from the point of view of graded manifolds. So I would like to start the talk by a brief refresher on graded manifolds, because as a member of this collective, I'm sure you have heard about Z-graded manifolds extensively before. So hopefully I can be brief on the introduction. Right. So when we know what are Z-graded manifolds, or what I mean when I talk about Z-graded manifolds, we can recall the definition of graded vector bundles, basically from the sheaf point of view, as a sheaf of locally discrete and finitely generated sheaf of modules of the graded functions of the manifold. Then we can give the sort of a new definition of a graded vector bundle, which looks much more like the definition you would see of a non-graded vector bundle. So we'll give the definition, then we will see how to move from one setting to the other setting, from the geometric manifold, graded manifold setting to the sheaf setting. And finally, if there is time, which if I have 60 minutes, there probably will be, we can talk about how the sheaf of sections, right, which is what I mean when I say a sheaf-defined vector bundle. I mean it's sheaf of sections. So we will define a sheaf of sections of a graded manifold in a somewhat abstract way, but then at the end we will see that actually it does correspond to graded smooth maps from the base manifold to the total space, which needs to be degree shifted. So we will talk about degree shifts for a bit, and then we can interpret sections of the graded vector bundle as we are used to, right, as maps from the total space, from the base manifold to the total space, which compose to the identity map when composed with the projection of the total space. Okay, so let's begin. When talking about Z-graded manifolds, if one doesn't simply want to jump and say the definition, which is entirely possible, but most people who haven't seen graded manifolds, assuming there is someone here who hasn't really seen a Z-graded manifold definition properly done, might get a bit confused. So I like to start, especially when talking about vector bundles later on, I'd like to start with a metaphor, not much of a metaphor, simile maybe. But what is the simplest smooth manifold? The simplest smooth manifold is just Rn. But we can think, like this will sound extremely dumb, but we can think of Rn, we can forget the smooth structure, we can just think of it as a vector space, a real finite dimensional vector space. And in order to make it into a smooth manifold, what we can do is we can choose a basis, right? We can choose a basis, then we take the dual basis, and that gives us global coordinates on this smooth manifold. As I said, we don't usually differentiate when thinking about Rn. We don't differentiate between the vector space aspect of this and the smooth structure aspect of this. But talking about grid manifolds, it will be useful, or I find it useful to think of those two things different. So, always integrated. So the first thing we need is the gradient analog of vector space. So we take something I know as this, right, where nj is a sequence of non-negative numbers. Negative numbers such that the sum over all integers j is some n, which is finite, right? So it's a sequence of non-negative integers, only finitely many of which are from 0. And this guy here is a sequence itself, the sequence of vector spaces, where for every integer, let's say ith component is a vector space, and what is it? Well, it's simply just this. Right, so the graded vector space is in this setting is a sequence of vector spaces, and the simplest vector space being Rn, the simplest graded vector space is something is this. Okay, so as in the stupid, silly motivation here, you would now like to move from this to a graded manifold. And now the step from this to a graded manifold will seem a little less simple. The first step is the same. From R and J, vector space, a graded vector space, we would like to move on. I will even denote it a little differently. I'll give a little g in front to signify that it's a graded manifold now, which is a graded. Same as before. Step 1, choose. And now the basis. I talk about the basis of this. Sometimes we say total basis, something like that. It goes from 1 to n, sum of all the dimensions of the component vector spaces. And what it is just you take all the bases of the component vector spaces and just smooth them together to get a set, and you call that the total basis. Each of these guys carries degree, right? This is, let's say, L. If I know if the vector is in the L component vector space. For our purposes, it will be useful to so I index these with little a's going from 1 to n, and we can split these two into a I. Oh, sorry. And we'll indices up. Those will be later when I talk about the rule basis. For now, I want the indices to be down. So we can just differentiate, say k I, and this has a degree 0, and k alpha, and this has a degree non-zero. So I goes from 1 to 0, the dimension of the 0th vector space, and I'll show. This is a great notation, probably not very, but alpha goes from 1 to n minus n0. We can denote this and why it's not a good idea. And tell it. Okay, so just split these two, denote those with the degree 0 by indices I, and those of degree non-zero with indices alpha. Okay, so we chose a basis. Now we move to the dual. basis. The dual basis being denoted as this. Again, A goes from 1 to n. Where was the dual of this? That's obvious. It's just the dual vectors. What's the dual of those that don't have a 0 degree? That's slightly less obvious, but every Ka, or n being alpha or I, right, with this being degree 0 or not, is a very linear map from this to real numbers, where we take real numbers as a graded vector space. And this can be a graded vector space, and the ith component is either R when I is 0 or is 0. That's, again, a bit silly, but it's nicely formalized. So this is a graded linear map of degree minus the degree of the map is minus the degree of the original basis vector, and how it acts on vectors here, well, that's rather obvious. It takes the basis vectors and achieves 1 when they are the same, 0 when they are not. Just a slight detail here, the degree of the 0 may not be 0. So the degree of this is the degree of KB minus the degree of KA. So if K upper index or lower index A, the fixed one, has degree 3, then K upper index A has degree minus 3, and the only non-trivial thing it does is map the vectors from the third component vector space to a number. From all the other component vector spaces, it needs to map to 0. So we moved to the dual basis. Again, this will be indexed by I or alpha, when this is degree 0 or this is degree non-zero. And the third sort of step, and this is not very rigorous, it's just a motivation of sorts. The third step is to define, we can now define what we mean by graded functions on this graded manifold. A graded function f is a graded function on the graded manifold GR and A. Various all completely fast. Again, it's not very precise definition, but f is now graded function on this graded manifold is a form of power series where the coefficients of the power series are smooth functions of R and 0, smooth functions in these variables, and variables of the formal power series are K alphas, are these non-zero things, non-zero degree things. And this is a shorthand notation. Okay, this is a I leave them with alpha. Probably this is one of the bestest. Which means that in the exam, okay, there we go. As it's K1 to B1, K and tilde to B.
We need to denote K I's as X I's.
Yeah. Here, and now it works, and it's F, B are smooth functions, the X I. So that's how we get coordinates on the graded manifold. The degree 0 coordinates here are just regular coordinates on R and 0 on the 0th component vector space. And the non-zero coordinates come here, or rise here, or we use them here basically as the variables of the formal power series. And we forget that they are, great linear maps. We forget that about them. We just keep their degree and treat them as a special symbol. But again, it's useful to still think of this as coming from there, because that will be used later on in the definition of the graded vector functions. Right, so now the sum of series is indexed, or it's summed over m of tilde tuples of non-negative integers, such that graded function, so it's a graded function, right? It needs to have a degree. So let's say that the degree of f is L. So this set over which it sums, that's the sets. There's that, I can just write it down to wave my arms around too much. So it's P1 to P and tilde. So that's the sum of B, J, degree, alpha here, okay, alpha goes through 1 and L. Because what I want is when I multiply two graded functions together, whenever I multiply two graded functions together, I want their degree, the degree of the product, to be the sum of the degrees. So in particular, if I multiply two graded coordinates, so a special example of a graded function, where you just leave one of the k's there. We get this, the degree of k b. So this here sort of forces every piece of this series to have the same degree, and furthermore, for this to be for this way to write f to be unique, we also need to impose this additional small thing that b alpha can be only 0 or 1 or a alpha. Right. If we have an odd degree and the second power of it, we get 0 because it anti-commutes with itself. So for this reason, we only allow these exponents to be 0 or 1 whenever the degree of the coordinate is odd. Okay. So these are the graded functions on higher graded manifolds.
Just a comment. Did you say how they are actually multiplied, or
I do.
how even
Yeah, they're multiplied as
power series?
power series.
Or Rudolf times.
Yeah, with graded commutative variables. So if it happens that these are finite, you just multiply them as polynomials. They're power series. You can write the prescription. It's not very.
Yeah.
I can put it.
No, right.
Yeah. What's important is that if you define the multiplication in the way that I want to say, you get that it's a graded commutative algebra. So f times g is -1 to f times g, multiply the degrees, g times f, so we get -1 or +1 based on the degrees of functions. Okay. Furthermore, for every open subset R and 0 of the base space, we can say, we can define these things where the coefficients are just smooth functions on the right, not on the whole set, but on the open subset, and thus we get a sheaf. It's not immediately obvious that's sheaf, but it's sheaf, and the sheaf is denoted as this. So for every u in open subset of R and 0, we get this, and this is a graded algebra of those things, of the graded functions. It's a graded vector space in particular, so it's a series of vector spaces, but additionally we can multiply elements of different vector spaces together so that they end up in this vector space, right? This tells us that we take something of degree f, something of degree g, and the product is in the space of degree f plus g. And so we get the algebra, rate commutative algebra, which is associated and has a unit. So, right, the 0-degree functions, one of the 0-degree functions is just one regular old-fashioned real number one. So this is we call this the algebra of graded functions, and so we call the sheaf itself the structure sheaf on this graded manifold, or the sheaf of graded functions, right? Or structure sheaf. And I say M. Why do I say M here? Because I want this to correspond to how many coordinates of certain degrees there are. If, for example, I want there to be M1 coordinates of degree 1. And that's why I denote it with this series. But if you take on the grade, if you look the grade dimension here, it's nj. So we have nj basis vectors for of degree j, but then we have nj coordinates of degree minus j, because these have opposing degrees to the basis vectors. So that's why here I say mj, where nj is n minus j. So the nj here, the n minus j, is the graded dimension of this as a graded manifold, while nj is the graded dimension of this as a vector space. Okay, so you see that now there's not fundamental, but there is a noticeable difference when we look at this as a graded vector space and when we look at this as a graded manifold. Right? I mean, you can define graded dimension of graded vector space to be the other way around, but it's not very natural. Okay, so why do I keep talking about this, or why is this so useful for me? Well, that's because same as Rn is, or open subsets of Rn are templates, smooth manifolds look like locally, so open subsets of this are a template of what graded manifolds look like locally. So we can, again, for every u, we can take, or I can now give the full definition of a graded manifold. So graded manifolds will destroy all of these numbers. The graded manifolds anyway. Pretty M is now double regular M and structure sheet. And this is a here. It's a second countable outdoor topological space over here, and this is a sheaf valued in graded commutative associative unital algebras. Right, so graded algebras, that have a unit and that are associative, that behave like this. Right, and when you switch the order of multiplication.
And do you stress on having local appearance the same as
This is not, thank you, this is not again. We impose that locally this, which is just unit an open subset of M. You can just restrict the sheep. You want this to look exactly like some open subset of Rn, C infinity. Okay, it's restricted to V, where V is an open subset of R M0. Yes, so this sheet, the structure sheet on M locally, and there needs to be an open cover such that this holds. Locally, it looks like that. It looks like these functions. But now we know what graded manifolds is. Of course, the notion of what this means is not entirely straightforward. It turns out to be, but it's not apparent that it is. Right, so if we have smooth manifolds, we would like to know what a graded smooth map is, right? We want aeromorphism between graded smooth manifolds, graded manifolds, sorry. So a phi, I'll go with this phi from n to n, these are graded manifolds, is an arrow in this category, it's a graded smooth map. We say if it's a double, where this underlined phi is just a continuous map between the space manifolds. It turns out that if you have an atlas on the grid manifold, it induces an atlas on the underlying topological space. So this always turns out to be a smooth manifold. So I will probably interchangeably use continuous and smooth here, because it has an implied smooth, both of these have an implied smooth structure. And this turns out to be smooth if it's only presumed to be. Okay, so we have a smooth map between the underlying manifolds, but that's not all. We also need to relate the structure sheets of the graded manifolds, and we do this by this. We call it pullback, but what it is, it's a sheaf morphism between the structure sheaf on the target manifold and the push forward structure sheaf, the source manifold. So this is a sheaf morphism, and there's one more technical. For every open subset, this needs to be an algebra morphism. It needs to preserve, to be linear and preserve the product. Furthermore, there's a technical requirement here that it preserves. These turn out to be locally ring spaces. So if you take the stalk of this sheaf, it's a local ring, and we need the induced map on stalks to preserve the unique maximal ideal. I won't write it here, but for this talk, it's sufficient to realize that this is a sheaf morphism, but there's an extra requirement. Interestingly, if it's an isomorphism, it automatically preserves the maximal ideal. So I don't need to stress here that this is a local ring space. It will become so because it's locally isomorphic to this. This is the local ring space. By the way, all of what I said so far and way more you can find in the large paper by Jan Wysocki. normal theory of graded manifolds rather than here. Right. Yes.
Can I ask you please one thing regarding the morphism?
Sure.
Because you were commenting that for the morphism between the base manifolds, you were saying something about smoothness and the fact that the map is continuous. I didn't quite catch that. Don't you need it to be smooth?
Yeah, sure. Actually, I don't, because so in the definition itself, it's sufficient to assume that this is a topological space, second countable Hausdorff, right? And if we have the structure sheaf to be locally isomorphic to this, then we can. There is a canonical way to obtain a smooth atlas on this underlying topological space, regular smooth atlas. It makes this into a smooth manifold. And then if we define morphisms between graded manifolds like so, with this only continuous, right? We assume this is only continuous, then it will turn out that it's also smooth with this smooth structure that we obtain from the graded atlas. And so we don't need to assume that. It follows from this being continuous and the other things.
Cool. Thank you very much.
So the breaks being local, that's, I can understand it as one of the reasons to consider discrete functions as opposed to, I don't know, something. Like if you compare it with super manifolds, the functions look different. So if I just try to copy everything from super manifolds just the way it is, the rings would not be local, right?
I think that the greatest motivation for this being the defined way it is so that this is a sheet. If you just I think so, right? So if you just sort of copy over from supermanifolds, that turns out not to be a sheaf. So in this way, this is a sheaf. I'm not sure if this needed to be changed somehow for the linked rings to be local, or if it already turns out that the rings are local here.
And the biggest, kind of the most obvious reason why we have to consider formal Poisson series is kind of if you want to actually evaluate locally those pullback maps, then if you don't consider formal Poisson series, you cannot pull back even functions because those kind of formal Taylor series you have to do there to actually calculate the pullbacks don't kind of truncate because your coordinates are not odd as in the supermanifold case where they always kind of eventually are zero. But here kind of you have to have these formal number series, so this doesn't happen. So you can really kind of do Taylor polynomials in these graded variables kind of as you wish.
Okay, so now that we are at least a little familiar with graded functions, graded manifolds, we can build on that and consider modules graded function, right? A graded vector space where you can multiply the elements, the vector space, by graded functions on the manifold. And if you do this for every open subset, naturally, so everything that's legal with restrictions, you get a sheaf of modules on graded manifold, graded modules. So a sheet of graded vector spaces. So for every open subset here, U is an open subset of M of the underlying space, the base space. This is a graded vector space. So it becomes S is a C infinity M module, or I sometimes shorten it like this to be precise. It's a sheaf of C infinity M modules. Depending on if, not surprisingly, this is a modulo of the graded functions. And the second one is that the restrictions on the sheaf are compatible with the restrictions on the graded functions, right? So if you take f times, I'll go with sigma, and restrict it to some v is the same as restricting the graded function and restricting the element of this. So these are sheaves of C infinity M modules. And now we need the notion of a frame for C infinity M module. Just a side note, I don't need to distinguish between left and right modules because I have graded commutative functions. So I can define multiplication from right as -1 degrees multiplication from left. So I'll just say module. Okay, so the collection of sigma I from some index set is a frame or S if the sigma i's themselves are local sections or elements of the biggest module, and for every open subset M, and for every tau from the small module, there exists unique unique functions fi such that tau can be written as a C infinity M linear combination of these elements with finite. Finite collection of graded functions such that this can be combined from these frame elements. So if this is true, then this is called a frame. If we have a frame, we can ask if the frame is finite or not. If it is finite, if F has a finite frame, we say that S is freely and finitely generated. We are finitely generated. Okay. Push the little less. Okay, I'll abbreviate this to F and FG future reference. Okay, this is still a bit too strong for us. We want S to be not freely and finitely generated, but to be locally freely and finitely generated. So if there exists an open cover of index set J such that the restrictions of the sheet, of the sheet is freely and finitely generated for every alpha, and we say that S, it looks like Y, S is locally freely and finitely generated. This is, so that's the definition, and this is almost what we can call a sheaf-defined vector bundle in a created manifold. We only impose one more thing, that the rank, the local rank of these guys is the same for every opening cover. Right, the created rank being the sequence Rj is the number of, I'm going to say, the number of frame elements of degree J. Graded rank. Another side note, for general graded algebra, if we don't think, we have seen infinity n modules, but if we have any sheaf of graded algebras, we can consider 8 modules. For general graded algebra, this may not be well defined. Different frames can have different corresponding ranks. But it turns out that sheaves of this modules, if the graded algebra is the graded functions, this is well defined. So every frame for the sheaf, the same rank, so we can call it the rank of the sheaf, and then we can want and we can impose the condition that all of these pre-finitely generated restrictions have the same rank. And so this leads to the definition graded vector bundles version. So we say that if M is graded manifolds and S is locally, briefly, and here locally, freely, and finally generated sheaf modules and create functions with those rank. Then this is the same thing by definition as saying that S is a graded vector. This is one possible definition of defining graded vector bundles. What you see here is basically the definition of the sheaf of sections of a graded vector bundle. So it's rather simple to define what we mean by sheaf of sections of graded vector bundles, not so much the other way around, defining the total space and then showing the sheaf of sections. It is not too much more difficult. It's the next part of this talk. Okay, so this is the sheaf version definition of a graded vector bundle. This you can find in
Just a small comment that this constant rank assumption is not really like necessary. It's like just for technical reasons because it has to be the same for each collected components. And anyway, so it just kind of prevents you having graded vector bundles which have different rank on each collected component of the base. But if you are fine with that, some authors are, you can ignore this assumption.
Right. It might happen that each connected component it has different ranks.
Sure. You can have in classical geometry, you can define vector bundles which allow it. Because it doesn't pose any technical difficulty, you just have to talk about rank
Okay.
more. The same with sub-manifolds, for example. You can have sub-manifolds which have different connecting components, and each of them can have different dimensions. So you don't care because so then consider point and a line as a summary.
Might be a good place to point out that smooth manifolds are a special case of graded manifolds. So anything that holds here needs to hold for smooth manifolds. Okay, so this is the sheet definition. Now, what's a bit new, well, not a bit new, slightly newer, is the other definition. Right? We want to define a vector bundle as a manifold, the way we usually do in regular smooth geometry, ordinary smooth geometry. We say that it's a manifold such that locally it looks like the base manifold Cartesian fit with a vector space and nice coordinates such that the transition maps are linear along fibers. Now the trouble with adopting this definition for graded manifolds is that if you restrict yourself to fibers of vector bundles, you lose some information, a lot of information. Okay, so this is a really good place for an example. Prototypical example of a non-trivial vector bundle is the vector bundle vector fields, right? So you say we can define vector fields on graded manifolds. You say that X is a vector field on a graded manifold M on some open subset U of the underlying space, not curly M. You can only if X is a graded linear map, such that it satisfies the usual graded version of the language field. Moves to F, that you times G, and then there's plus, there's the sign factor. If we move X to F, the sign we need to get here is the degree of X times the degree of F, X. So we can define vector fields algebraically. Simple. This turns out to be locally freely and finitely generated and of constant graph, same as non-graded geometry. We know that if we have X, let's say XA, which will be XI, X, mu, right, alpha, that's alpha. These will be local coordinates on M. All of them, these will be the coordinates of the degree 0, and these will be coordinates at non-zero degree. So if locally we have these coordinates, M, by this I mean that we have the local isomorphism of M to that prototypical space that we talked about at the beginning, and the coordinates there through this isomorphism give rise to these coordinates, which are now graded functions of M in infinity, curly M, U, alpha, whatever. Okay, I had alpha for the cover, right? So I'll give you. Okay. So if these are coordinates, then locally X always looks, again, this looks the same as in non-graded geometry. XA is small x, to d over d XA. For these coordinate vector fields, XI, if you let these loose on the graded function that I erased here, but you can recall the formal power series. Right, so this just acts on the smooth function coefficients, and like ordinary partial derivative, and this, the graded functions, is basically defined to give 1 when it encounters the same coordinate and 0 otherwise. and then extend it through this to act on the entire series. You need to verify that that makes sense and that it works, but it does. So locally, every vector field looks like this. So this is the local frame. These are the local frame elements for vector fields. So this is the locally finitely generated sheet of C infinity n modules, and the rank of it is not the same as the dimension of the graded manifold, but and there's a minus here because this coordinate vector field is minus degree. Okay, there's a typical example of a graded vector field. Now, why did I say that you can't restrict yourself to parameters when talking about graded vector models? Because there is a nice counterexample to most things about vector fields regarding graded manifold, and that's the Euler vector field. There's a vector field on every manifold, globally defined, such that when you let it loose on the graded function, it returns the degree of the function times the function itself. You can verify that this is a vector field, that it satisfies level 2. It's a bit weird. In the non-graded case, if all the gradients are 0 except the 0th gradient, which, in other words, in ordinary smooth geometry, this is the 0th vector field, because this is always 0. So this is a purely graded aspect. But if you value this vector field at some point x of n, tangent space of the graded manifold, this is 0. Because E in the coordinate expression looks like the degree of the coordinate d over d, the coordinate, and valuing a vector field at a point literally means valuing this function. And if you value any function whose degree is other than 0, you automatically get 0. It's from the definition of what it means to value a graded function. But these are non-zero only if their degree is non-zero. So this is 0.
So maybe I have a very stupid question, but how do we know that in this graded case we end up having only these linear maps as differentials in this puzzle? Why there's no another choice for?
Right. Yes, that comes. Basically, so if I understand correctly, the question is why can we write every vector field like this?
Yeah,
Or
probably yes.
yeah, but there are no other graded derivatives than C infinity and linear combinations of the coordinates. Right. So that comes from actually a nice proof. It relates to what I was saying before. So you can take any graded function, and you can split it, basically do a Taylor polynomial, or Lemite is called in the paper, and so you get a polynomial in the graded or non-graded degrees, and then you get something that is in the n plus first power of an ideal of non-invertible functions, basically. So that way you can say
It's the same proof as for ordinary particles from manifolds. It's completely the same.
Okay.
So it's standard that you have some. It looks incredible that every first order derivation looks like this, but
Yes, but in graded sense, I would expect that there might be any mess
no,
appearing.
there is no mess.
Okay.
Except maybe my proof is not correct. Then that's perfectly possible. You are welcome to. But I
Okay.
the same.
Okay.
yeah, I think that the proof goes like you put this like this act on a function and this, and you show that what remains is in the n plus first power of non-zero functions for every n, and the only function that satisfies this is the zero function. So this needs to be equal for every function. Right, so this just serves as a motivation that we can't just take the usual definition, graded vector bundle, and a non-graded vector bundle, and just say everything is graded and go with that. Okay, so I have been talking for a long time, haven't I?
Let's say about 10 minutes left, or
10 minutes left.
because we started a bit later.
All right, so I'll probably just give the definition of the graded vector bundles from the geometry point. All right, so as in the beginning, right, we talked about the difference between R and J as a graded vector space and as a graded manifold. They are now sort of different. Same way, if you look at yeah, R and J, right? So we get back to this, and you can interpret addition of vectors as a graded linear method of 0 from R and J. J is defined component wise to R J again. Yeah, apologies, this seems a bit too silly, right? This is just you take two vectors and you add them together. This is you take a vector and you multiply it by a lambda. It's a real number. So these are maps, this as a vector space. So we would like to interpret them as graded smooth maps on this as a graded manifold. So now to do this, so we go from these to sigma from graded manifold corresponding to the graded vector space, and as a product of graded manifolds, J to itself, and for every lambda you want this graded map. I can do that. It is a short. Basically, you want graded smooth functions. So what you need is the map between the underlying smooth manifolds, which in this case are R and 0, and R and 0, R and 0, and then you need the pullback of graded functions. Again, it turns out that to define a pullback when you have global coordinates here, to define the pullback on every graded function, you just need to define the pullback on the coordinates themselves. And then it uniquely extends to every graded function. Is my a very useful thing. Okay, so the underlying smooth maps are just right. This is the regular plus map on R and 0. And the same thing for the underlying smooth map lambda. I'll write it counterwise here just on R and 0. And on the pullbacks, you define right, pullback of a coordinate here. We know that we have global coordinates here. We call them Ka, for example. So this is defined again as you might expect, like so. Because on the product manifold, again, some discussion about good product graded manifolds would be in order. But on the product manifold, if you have global coordinates here, called Ka, then you have two sets of the same global coordinates. You go to them as K1a and K2a, and define the pullback of this function like so. And H lambda pullback Ka, not surprisingly. You just look at ordinary sum, you look what a pullback of coordinate looks like, and then you go back here and you define it like so for the graded case. conceptual difference is that now these are graded smooth functions with their manifold. And so the goal here is to define graded vector notice to be graded manifolds. But locally, again, the product manifold acquired of the underlying smooth manifold and this G, R, and J manifold. Okay, and then to go ahead with this definition, we need a notion of a fiber-wise linear map in the graded manifold setting. So that's why I need to convert these two maps to graded smooth maps. But now, so now I can say that if you have the graded smooth map, graded manifold, region times our favorite graded manifold to n times this, and you have small phi between m and n, then you can say that phi is fiber-wise linear over small phi is fiber wise linear phi if, and then you just draw nice commutative diagrams. So if you move through phi here to target, or you can project the first manifold and move small phi, and project here, this needs to be the same. So this needs to commute. First thing that needs to commute. The second thing that needs to commute. So far, this says nothing about linearity. If you think of this as ordinary smooth maps, this says nothing about linearity. This says that it doesn't. That the first point gets maps according to phi. But now, the second diagram you impose, or you want to commute, is phi and times G. This one, you take the identity map and you can compose the product is with the multiplication by a lambda map. J and these two together mean that big phi is the different bond phi is fiber-wise linear over this one phi. Okay, be literal, this means that it's fiber-wise homogeneous. In ordinary geometry, this would mean that phi and lambda v equals lambda phi m lambda v. Okay,
Ja muss ich teda představit phi ve dvou komponentách.
yeah,
Musíš tam představit phi od dvojice MB. A vždycky byla do dvojice. Máme phi M a nějaký phi hvězdičkou
yeah.
V. MB, teda. závisí tak. A to tady těžko ani nevydáš.
Děkuju. Right, this is homogeneous. Fiberized. Homogeneous, but a nice little observation. It's true that it holds that if these two commute, then it's also fiberized edited always. You can see that from the local component. You basically look at from these two diagrams in terms of the local shape, the pullbacks, and you see that they become fiberized edited as well. Corollary of this is something I didn't know. Nice observation that if you have finite dimensional vector spaces and you have a smooth map between them, which is homogeneous, it needs to be edited. So it needs to be linear.
This is what I didn't get in CERN, actually, so.
Yeah.
Okay. And Bill, we have phi as well, I guess.
Yes. Okay, and now I can finish with the definition of the gradient vector Rudolf. Let's see if I can fit it here. Okay, so we have two graded manifolds. I know this looks like sigma with E and M. These are graded manifold. Then we have a graded smooth map from E to M. Then we have a collection of graded smooth maps for every real number that go from E to E, and these together act that are related like so. Okay, so this is all the information that we have, and we say that the quadruple here E M by H lambda R is a graded vector bundle is a graded bundle. That's not all of it, but we need it locally to look like that. So if there exists open cover U alpha M together with isomorphisms. This is a bit long. It's actually an elegant definition, you can see. Together with isomorphisms and alpha times R J. That, so locally, this space is isomorphic to spread manifold, as we would expect, such that two things commute. First of all, these are preserve the fibers, I would say. So U alpha times G R J to E. Psi alpha here is the same, and going phi here is the same as going through the first projection here. So expected. And the second one, we need this to commute. And finally, we need this to commute. Okay, go to E. And then if we go by this map again to E, the same as going this map that we have on CRJ. Here. This means that locally these maps look like multiplication by lambda. We call them the homothetic maps on E. Right, so if this all commutes, then you say that this is a great vector bundle, and you are happy because you have finished your definition. Okay, now I'm probably going to stop the lecture here. It's a little too carried away at the beginning of the great manifolds.
I got to the best of us.
So thank you very much for making us happy. Here comes the space for your questions.
And so it's cool that you can do this. What are any like nice applications of this point of view? Is that, I mean, I just naively imagine that people will like to start with a sheet theoretic picture. Because usually if you go to graded manifolds, it's because you want to work into functions and everything. Yeah, so is there any concrete problem you can tackle with this point of view?
I don't know what problem, but I have a general example I had prepared. So a nice thing you can do with this point of view is pullback bundles. Pullback bundles and geometry and the sheaf way in gray geometry are quite ugly, as I understand it. You need
Ugly, but need some work.
It's something. The word used was you need to sheafify something that's not a sheaf in order to get a sheaf. But here, if you have vector bundle over some n's, and you have a graded smooth function from m to some n, then you can define the pullback bundle very straightforward, like fiber product phi with E. And from the universal properties of this manifold, immediately follow that this is a pullback bundle. See what that. So the nice thing about this, you can define, this is how you define the H lambda, the homothetic maps. That's on this. Because you use universality, obviously. So you have this, then you have E. You have M, the pullback diagram, right? Cartesian square, or all the names that this has. This is phi, this is phi, this you call this, and you start to define the product projections, which come with the definition of this. And you define the H lambda on this base just by putting an arrow of this and calling it phi hat, saying that this is the same as this, and putting an arrow here and saying that this is H lambda on E composed with phi hat. And you immediately get homothetic maps here. I think this is quite perfect. Another thing where you use vector bundles, very vector bundles, stone spaces. We just talked about this this morning, Sarah, is when you define form of connection on the graded principle.
Essentially, the answer to this is that there are some parts of graded geometry where it is you really have to work with arrows and commutative diagrams of graded smooth maps, especially where graded geometry and linear algebra kind of meet. So, for example, if you want to, we needed to think about, for example, representations, graded groups, because you want to have some Lie group action. which we can only define using commutative diagrams, because for our graded group are just lead group object in our category of graded manifolds. Therefore, we have everything only in terms of maps. And suddenly you start talking about something which is linear somehow. And the way how to do it is, for example, that you look as things as maps into some vector bundles or trivial vector bundles and say, okay, this commutes with this motility map, and then you have your linear things. So you can, for example, define representations of graded groups using this kind of language of vector bundles as manifold, because you need completely diagrams, smooth maps, which you don't have in this algebraic picture. You don't have you have them, but you have to dig them out first.
Any other question?
Maybe I would like to ask, because you probably said it, but I missed it. What's the phi hat of M map, this linear map doing? How is it defined?
Phi hat.
It's, yeah. No. The other phi, it's still in the blackboard at the top.
Yeah.
No, the blackboard you were, no, the one at the top.
Oh, okay. Here.
Yeah.
Right. So, because I just talked about the interpretation of this diagram. I think if these are just smooth maps, you forget G here and the thing here. On Blackboard before I erased this, we saw that this looks like this for some map, which depends on M, and this diagram then imposed that this map is homogeneous, like so. And because we have a diagram, I'm making this up, we have the diagram n times, let's go with Rn, n times Rs, R, this was the phi, this was the projection, this was the projection, and this was M multiply N. So we know that phi takes some M and V. And we know that this is again some double, something and something. And we know that if we project this thing, it needs to be the same as taking M and having it by phi. So A needs to be phi or M. And right, so basically, with this in hand, we can define a map phi M hat from R to Rs for every M here, just by taking the second projection of phi M. Example, I guess. So this would be this. If I'm not mistaken. Okay, so this is the definition of the phi hat, and this diagram then says that phi hat is homogeneous.
All right. Yeah, cool. Thank you.
I would have a question. You said at the beginning some definitions around great bundles or great manifolds, and continued with the notion of sheaf with values in some C infinity modules. What might bring us to the realm of greater vector bundles viewed in the very narrow sense of those sheaves. And this is the direction of geometers as well. But you've ended with more, say, traditional definition of greater vector bundle. So have you been motivated by the original say ground you came from, meaning that is there any good notion of the graded vector bundle in sense of graded sheaf or sheaves with values and C infinity modules and some extra data, or is it some ad hoc definition not much related to
Like you mean this one?
yes, because you have here something what looks more similar to geometers who do the ordinary differential geometry and work with vector bundles. But on the other hand, you can come here as well when you regard your definition of graded vector bundles genuinely in the realm of sheaves, right? Some people from algebraic geometry might correct me, but I think it has something to do with coherent sheaves, which are equivalent to the category of vector bundles. I'm not wrong. So is it the correct way how I can see this relationship, or
Yeah, I would say that my motivation was a bit more basic or simplistic, because when we have ordinary vector bundles, we know that we can work with the total space or we can work with the sheaf of sections. And those two notions are equivalent in the sense that the categories of them of these defined geometrically defined vector bundles and the sheaf defined vector bundles in the, I guess, narrow sense from some abstract point of view of just locally free and finitely generated modules of smooth functions on manifold, that the categories are equivalent. So my motivation was to see if the same thing holds in graded geometry. So I made up this definition, and turns out it holds.
okay? So for instance, this homotheticity property somehow popped out automatically.
Yeah, well, we discussed this with Jan. We tried to simplify the definition as much as we could. And a pleasant surprise to me was that we can forget the plus maps, right? The addition of vectors. We can just forget about it. It's not important because it then follows just from these homothetic maps. And another thing that with these homothetic maps, if we include them in the definition of the vector bundle, then to move from this setting, from the graded manifold to the sheaf setting, right, to construct the sheaf of sections of a graded vector bundle, it's very, very simple.
Okay.
It's just you take a sheaf. I can write this down in 1 second. You take a sheaf, so also nothing extremely new, sheaf of linear functions, of functions linear in the fiber of the total space. You define this as the intersection over every number, and then you have pullback by the homothetic map minus just multiplication by lambda.
Okay.
This is a lovely answer. There's a current here. And so this just means that when we pull back the map by it gets multiplied by lambda.
Okay.
So this is a lovely, easily defined sheaf, and then you just say that the sheaf of sections on E is the dual of this guy. And that's it. That's the sheaf of sections.
Okay.
And then you show that this is a graded vector bundle in the sheaf in line sense. The map E gets matched to gamma E is a functor, and that it's essentially surjective, only faithful functor, stuff like that. But yeah, including the H1 map make this very easy in the definition.
Okay, cool.
Maybe a quick question. So here we have the graded vector bundles. So how far are you from graded principal bundles or something like that?
Not far.
Yeah, this will be the next paper then.
Next thought.
Yeah, but we have a graded principal bundles which are, that's also one of the reasons, because we have Rudolf wrote a master thesis on graded principal bundles. We have the definition, which is on the geometrical side, because we had some difficulties to kind of invent some fully algebraic definition of graded principal bundles. So we didn't do geometrical ones. So for us, graded principal bundles are graded bundles in this
Is the same as
which-
no graded here.
so and you add some G-equivalence conditions and you get your principal bundle definition. And then we have also notion, already we have some notions of connections and
Because if you're looking for an algebraic definition of a principal bundle, you could try to use the Hopf-Galois property. This at least like in classical differential geometry, that's a correct thing. So maybe there's a graded version of Hopf-Galois.
yeah, certainly there is some version of it, but there's no reason for not to work, right? If it works for a competitive setting, it will also work for a graded competitive setting. So yeah, but we have some notion of graded principal bundles. But just not the algebraic ones, but it's still can be done.
Is there any other question? If not, let me thank the speaker again.